So welcome you back to today's lecture. So what we were doing was we were discussing about Bayes and Minimax estimation. So what we have is we have a risk function for any estimator delta, which is a function of a theta. So what we do in the Bayes estimation is we consider theta to be a realization of some random variable S having PDF or PMF Fs, and we define the corresponding measure by pi. So what we had realized was there is a problem in minimizing the risk function for every value of theta. So what I try to do is we try to look at some characteristic of the risk function which does not depend on theta. So one such characteristic we saw is if we have some prior information from our past belief about the unknown state of nature, I try to quantify that in terms of a probability distribution or the PDF or the probability measure, and let that quantity as a random variable is denoted by S. So then rather than considering R delta theta, I say that what is the average risk when average is taken over the randomness which is there in the unknown state of nature. So we talked about the Bayes risk of an estimator delta, which is the average risk. Now this is called the frequentist. This is also, we may say, a classical risk where no prior information is there. So what we do in the finding a Bayes estimator is we try to minimize this. Then we saw that in the Bayes setup, we have two sources of information about the unknown state of nature. One is through the prior information, and one is through the data. So you have a two distribution, prior distribution of Fs theta, then F theta x, which is the distribution of the data x, given that theta is the true state of nature. Then it makes sense to update the prior information in the light of additional information which you have, which is contained in the data, which amounts to considering the posterior distribution. Then we realize that, okay, for Bayesian analysis, it is the posterior distribution which plays the vital role. The rest of the things don't matter. And that is what exactly happened, that we realize that if you have to find a Bayes estimator, just find a Bayes action. And what is a Bayes action? The one which minimizes the posterior risk. So try to minimize the posterior risk, and then you will get one action which you call as a Bayes action, which will always be a non-randomized estimator. Then we were studying various properties of Bayes estimator, but before that we thought that sometimes it makes sense to even talk about improper priors. Improper priors means pi is not a probability measure, or in other words, integral over d pi theta does not integrate out to 1, rather it integrates out to infinity. So like I said, that one may be interested in a non-informative prior in interval AB, which would be uniform distribution on interval AB. Now if one has to extend uniform distribution over the whole real line, that means A going to minus infinity and B going to infinity, that amounts to considering the Lebesgue measure on the real line. So that means your d pi theta is nothing but integral over theta d theta. Sorry, pi of A is nothing but integral over A d theta. So I can talk about the Bayes action even in those situations, the Bayes estimator in those situations where pi is not a proper prior distribution, or in other words, integral over whole theta d pi theta is infinity. Now we call such a Bayes estimator to be the generalized Bayes estimator. So generalized Bayes estimator is nothing but a Bayes estimator corresponding to improper prior. Improper prior means its whole integral over the parameter space is infinity. Then we talked about what are admissible estimators and what are inadmissible estimators. So we said that an estimator is said to be inadmissible if I can find an estimator which dominates this estimator. When I say an estimator dominates a given estimator, that means I can find an estimator whose risk is always less than or equal to the risk of a given estimator, which is inadmissible, and there is a strict inequality for some theta naught. And I say that any estimator which is not inadmissible is admissible. Then we also realize that admissible is a desirable property. That means any good estimator should be admissible, or in other words, it should not be inadmissible, because if it is inadmissible, you can find a dominating estimator, so that should not be considered. So admissibility is a desirable property. But then we realized that all admissible estimators need not be good estimators. So blindly considering the admissible estimators may not be a good thing. And we saw that any constant estimator, if you consider, that is an admissible estimator, but that is not something which is desirable, because a constant estimator does not use the data at all. So it just guesses, it just gives you one constant. You whatever data you observe, I'll estimate the mean by 0, which is nonsensical. So although the constant estimator is admissible, but it is very nonsensical. So the point being emphasized is that admissibility should be a property which should be possessed by any good estimator, but any estimator which possesses this property need not be a good estimator. Then we were studying various properties of Bayes estimators, and the theorem which we were doing says that your Bayes estimator would be admissible in various situations. So let us write down. So this is a theorem which we were doing last time. In fact, the first two parts were done. So suppose delta pi is a Bayes estimator with respect to prior. The first result says if delta pi is unique, then it is admissible. When I say it is unique, it means that if there is any other Bayes estimator, let us say delta star, then delta star would be same as delta pi almost surely, and this almost surely is with respect to conditional distribution of x given theta. Or in other words, delta pi is equal to delta star almost surely with respect to distribution f theta for every theta. So any unique Bayes estimator is admissible. Now what we had seen is when your square error loss you are considering, then the estimator which you get as a posterior mean is the unique minimizer. So that means under square error loss function, the posterior mean will always be admissible, an easy consequence of that. Then we did a second part where it said that if theta is countable finite or infinite, and your prior is such that it gives positive weight to every singleton, then this implies that delta pi is admissible. So very nice. And the third situation, what we saw was, so this I had proved, this was proved, and what we were trying to prove yesterday was, where we left was, suppose theta is a subset of k-dimensional Euclidean space, and theta is open. And my prior is such that pi of b, that means prior is such that it gives positive weight to every open set b, for every open set b, which is subset of theta. And for any delta belonging to the class of all estimators, for which or for any delta belonging to for which r delta theta is finite for every theta belonging to theta. R delta theta is a continuous function of theta. So roughly basically this condition is saying that your prior is such that it gives a positive weight to every open set. Not only that, its risk function is always continuous. Risk function of any estimator is always a continuous function of theta. Then this implies that for every, this implies that delta pi is admissible. Now this is one of very useful result in proving admissibility. So let's try to prove it. A and B we have already proved. Let us try to prove the part C. Now, whenever you have to prove admissibility, it's always better to start with counter hypothesis. So on contrary, I assume that delta pi is not admissible. So on contrary, suppose delta pi is not admissible, that means it is inadmissible. What does that mean? That means there exists an estimator delta star which dominates this. So that means there exists, that is, there exists a delta star which is an estimator such that R delta star theta is always less than or equal to R delta theta for every theta belonging to theta. And there is a strict inequality at some theta naught. So R delta star theta naught is less than R delta theta naught for some theta naught belonging to theta. So that means this difference is positive. R delta naught theta naught, R delta theta naught, sorry, this would be delta pi. That means R delta pi theta naught minus R delta star theta naught is positive. So let me put that quantity as epsilon. So let R delta pi theta naught minus R delta star theta naught is epsilon. So that I know my epsilon is greater than 0. Now I define a set B which is collection of all those thetas in capital theta such that this risk difference is greater than or equal to epsilon by 2. Now epsilon is bigger than epsilon by 2. So if this risk difference is greater than epsilon by 2, that means theta naught would belong to this set. So this collection of all those theta belonging to theta such that R delta pi theta naught minus R delta star theta naught is greater than or equal to epsilon by 2. Now let us make few observations. First thing is B is not equal to phi. Why? Because theta naught clearly belongs to B. Because if theta is my theta naught, this difference by this equation is epsilon, which is greater than or equal to epsilon by 2. So theta naught always belongs to this set. So B is not phi. Second thing is I look at this difference. For any risk for which risk is finite, for any estimator for which risk is finite, and that is the case over here, otherwise it cannot be epsilon, this is a continuous function of theta. So I put it over theta. If it is a continuous function of theta, what is a B? B is basically the inverse image of epsilon by 2 to infinity. So I can put here, if you want, greater than epsilon by 2, not greater than. Even then, B is non-empty. So this is basically the set where this difference takes value epsilon by 2 to infinity. So basically, this is nothing but the inverse image of the set epsilon by 2 to infinity, and inverse is taken under this convex, sorry, this continuous function, R delta pi theta minus R delta star. And you know that continuous functions, for continuous functions, inverse image of an open set is always open. So epsilon by 2 to infinity is open in real line with the usual metric, and r delta pi theta minus r delta star theta is a continuous function of theta. This implies that inverse image of this set under this continuous function, which is nothing but set B, would be open. What does that mean? My priori says that pi of B is positive for every open set B. So pi of B is positive. Good. So now I'm almost done. So now what I do is I consider r delta pi theta. I consider their base risks, in fact. So I consider r delta pi minus r delta star pi, which is nothing but integral over theta r delta pi theta d pi theta minus integral over theta r delta star pi d pi theta, which is nothing but integral over theta r delta pi theta minus r delta star. Sorry, this should be theta. R delta star theta d pi theta. Now I break this theta into B and B complement. B is the set where it is greater than epsilon by 2, and so this is same as integral over B of this plus integral over B complement. Right? If you want, you can write down B, yeah, B plus B complement. Now note that r delta pi minus r delta star theta is always greater than or equal to 0. R delta pi theta minus r delta star theta is always greater than or equal to 0, whether in B or B complement, always. So in B complement, the integrand is always greater than or equal to 0, pi is a measure, so this quantity would always be greater than or equal to integral over B r delta pi theta minus r delta star theta d pi theta. But on the set B, what is happening on the set B? On the set B, this would be theta. I have put a theta naught. So the collection of all those theta such that r delta pi theta minus r delta star theta is greater than epsilon. So on the set B, this quantity is always greater than epsilon by 2. So that means this integrand is always greater than or equal to epsilon by 2. So this would always be greater than or equal to epsilon by 2 integral over pi d pi theta. But what is this? This is nothing but epsilon by 2 pi of B. Now my choice of epsilon is positive. Pi of B being open, this is also positive. So this is positive, this is positive, this is greater than 0. So what do you conclude? You concluded that r delta pi is always greater than r delta star pi. But delta pi is base. So it would have the smallest base risk. So its base risk cannot be larger than the base risk of any other estimator. And that is what is happening over here. So that means I get a contradiction. So this contradicts the fact that delta pi is base. So I assume something contrary to the hypothesis, and what we get finally is something which is not true. So that means what we assumed in the beginning is not correct. So that means delta pi is not inadmissible, which means that delta pi is admissible. So very useful result. Now, this is one of the advantages of a Bayesian analysis. That Bayesian analysis not only incorporates the prior information, but sometimes it is also useful in establishing admissibility of a given estimator. So Bayesian analysis, whether one agrees or not, so Bayesian analysis this is always useful in establishing admissibility. And in fact, if you look at last theorem, it says in many situations Bayes' rule or the Bayes estimator is an admissible estimator. So if one has to generate admissible estimators, one can do so by deriving Bayes estimator with respect to various priors. Now if you have to prove some good estimator is a admissible estimator, one may try to find out a prior corresponding to which the given estimator is Bayes. And in most situations where these conditions are satisfied, such a Bayes estimator would be admissible. Now the question arises is, can I do the same thing for generalized Bayes? Now normally these generalized Bayes are the limit of the Bayes estimators. That means in the prior you take parameters and take their limit. Then the estimator which I get is normally a generalized Bayes estimator. So generalized Bayes estimator, first of all, it is corresponding to an improper prior, and normally in limit it is a limit of a Bayes estimator. And normally we have seen that Bayes estimator is admissible. So normally I would expect generalized Bayes estimator is admissible, but in general a generalized Bayes estimator may not be admissible. So a generalized Bayes estimator may not be So what one may be interested in looking at is what are the conditions under which a generalized Bayes estimator is admissible, because then I would have an additional tool where I can check an estimator is admissible or not by verifying whether it is generalized Bayes or not. So the next theorem which I'll do is will give you conditions under which even a generalized Bayes estimator is admissible. So let me write down that theorem. Now note that what this theorem says is, although it looks theoretical in nature, but what it is conveying is a very simple thing. You see, what does a Bayes estimator does? Bayes estimator minimizes the average risk. So it is minimizing, in certain sense, average of a risk. So that means it will be minimizing risk at some thetas. So in other words, Bayes estimator normally would be such estimator, it would be minimizing risk at some points, because it is on an average minimizing the average. Now if that is the case, then it cannot be inadmissible, because inadmissible is you can find an estimator whose risk is less than or equal to risk of a given estimator for any theta. Now here Bayes estimator, like a constant estimator, may be minimizing risk at certain thetas. So the way constant estimator are admissible, Bayes estimator are admissible. The argument which I gave is a very heuristic argument, that it is, since it is minimizing the average, I would expect that there would be some point around which the average is centered, it would be minimizing the risk. Okay, so nothing very surprising that Bayes risk is admissible normally under certain conditions. Now let's do